Okay, so it says, suppose you want to construct a polynomial that's equal to natural log of x, and we centered, on the other page, we centered natural log of x at 1, I believe. So we're going to find the general term, and then we're going to figure out what's going to happen at when x equals 2 in our series. So let's, well, I guess from memory, this was our fourth degree, let's say our nth degree polynomial. It was x minus 1 to the first over 1, and then, actually, I can't remember now. Let's go back. So then minus x minus 1 squared over 2. Let's see. I'm going the wrong way. Minus x minus 1 squared over 2. And then did it alternate, or was something weird happening? Oh yeah, so it's alternating. So easy. So x plus x minus 1 cubed over 3 minus x minus 1 to the fourth over 4. And I think you guys can figure out what the general term is. So it's alternating. So negative 1, the first term's positive. So we'd start this at, n equals 0 on to infinity. If I could fit a summation in there. And so then I have x minus 1, go away, x minus 1 to the n plus 1 power, right? Because if I'm starting it at 0, I need my first one to be to the first over 1. So that works over n plus 1, and there's not even a factorial in this, right? So that's my general term. Now I'm going to erase some of this so I can make room for the series. So once I got the general term, let's figure out what the series would be. So this is natural log of x. We're going to say it's equal, but it's not, probably not always going to be equal to this. So n equals 0 to infinity of negative 1 to the n, x minus 1 to the n plus 1 over n plus 1. All right, just double check when I plugged in 0, first term's positive. So yeah, it all works. So now I can get rid of this. Okay, so what they're saying to do is, let's plug in 2 into this and see what happens to this series, because I'm thinking if I go on forever, maybe this series will converge to natural log of x. Or natural log of, or maybe they'll be the same thing, I guess, is what I'm trying to say. So we're going to substitute in 2 for x. So if I do that, this series becomes negative 1 to the n, x minus 1. So 2 minus 1 is just 1 to the n plus 1. Well, that's just 1 over n plus 1. Well, what do you know? That's an alternating series, right? And so you could say, well, that's alternating. A sub n is 1 over n plus 1. A sub n is positive. Yep. A sub n is decreasing. Yep. And the limit of a sub n as n goes to infinity is 0. So this is convergent by alternating series test. So it's actually going to be conditionally, oh, keep hitting that button. It's going to be conditionally convergent, because if you took the absolute value of this, you're left with 1 over n plus 1, which you could do limit comparison with the harmonic and prove that that's divergent. But regardless, this thing converges when x is 2. So we're going to say that this is exactly the same thing as natural log of 2, but the issue is we can't really add up an infinite number of terms, right? But if we added up a bunch, maybe we'd be really close, okay? All right, so recap, we have 3 of these memorized. So sine, I remember that that's an odd function. All these start at 0. Negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. E to the x, I remember that's the easy one. All start at 0, that's just x to the n over n factorial. Cosine, that's going to be negative 1 to the n x to the 2n over 2n factorial, and I just remember cosine's an even function, degrees are even. Okay? All right, so natural log of x plus 1, I actually can't remember it off the top of my head. We'll come back to that. So look on the answer key, like that one's not used as much as the other three, but that is one that you're supposed to know. So I'm just going to write see the answer key to get that one down, and I'll write it up on the board in class. Okay. So the point is, or I guess the question is, why are we even doing this? Like thinking back to cosine, these are very good approximations for the functions themselves, usually, you know, very, very good near the point of tangency or the center, because it's not really a tangent line anymore. And a lot of times you only need an approximation for something. So this random factoid in here, you only need 39 decimal places of pi, which a lot of you remembered way more than that in middle school. You only need 39 decimal places of pi to calculate the circumference of the known universe to an error less than the width of one atom. I don't know how they found that out, but you know, it's written on the page, so it must be true. Okay, so they're asking us use the three-term Maclaurin polynomials to approximate the following and then determine the error of your approximations. So you can actually do this because you have a calculator. So we're going to eventually be able to find the max error, maybe if it's an alternating series, or maybe, you know, you're going to have to use something that you haven't learned yet, that you'll learn on the last day, called the Lagrange error bound. Okay, so I know that cosine's polynomial, so it says three-term. Well, the third, I know you probably don't have this memorized yet, but the third term in cosine is degree 4. So I'm going to call this p sub 4 of x. That's 1 minus x squared over 2 factorial, which you don't really need the factorial, plus x to the 4th over 4 factorial. Okay? So I want to find cosine of 2. Well, cosine of 2 is approximately p sub 4 of 2, which is 1 minus 2 plus, what's that? 2 times 2 is 4, 8, 16. 16 over 4 is 4. 4 over 2 is 2. Is that 2/3? Did I do that right? I think so. All right, so then that's 1 minus 2 is negative 1 plus 2/3, so that's negative 1/3. All right, so I've approximated cosine of 2. I'm saying it's about negative 1/3. Which is actually pretty cool, because if I just asked everybody in class what's cosine of 2, nobody really has an idea, but now we can at least get, you know, a number. We're not really sure how accurate it is yet, but we're about to find out. So if I wanted to figure out how far this was from the actual value, I could just, since I have a calculator, I'll take p sub 4 of 2, subtract, you know, cosine of 2, and then take absolute value. So I actually don't have a calculator because I'm not prepared. But if you did that, you can get the error, and it's actually pretty darn close. So this is kind of getting to the question of when are these accurate, when are these not accurate. So if we did natural log, I'm not really sure which. I guess we would use whichever one I have up here that I couldn't remember, because this is centered at 0, but it's going to be an approximation for natural log of x plus 1. So it looks like I'm changing the center here, but I'm not. I would take derivatives of this function and build the actual polynomial. But this is centered at 0. So when I plug in, you know, I have natural log of x plus 1. So I would plug in 0.5 into this to come up with the approximation. Well, over here, if I'm using the polynomial for natural log of x plus 1, I would have to plug in 2 into it. So I'm getting further away from the center, which there's no way for you to know how bad of an approximation it is yet, but what ends up happening is this approximation is going to be a whole lot closer to the real deal than this approximation. And the reason is that we are moving away from the center. Okay? Which I think you guys already get the idea. Same with a tangent line. If you have a tangent line to a function, near the point of tangency, we're pretty good at approximating function values. The farther we get, the worse our approximation is. So that's what they're trying to get across here. All right?